Okay, so let's start. So probability density function. So starting with probability distribution function. So probability distribution functions describe how probabilities are distributed over the values of random variables. So it is just a depiction, or we can say it as something which describes how the probabilities are distributed over the values of random variables. And as we saw earlier, random variables basically are of two types: discrete and continuous. So similarly, if we try to understand this topic, we have to cover how random variable, like how probability distribution function is defined in case of random variable and continuous variable. So in case of continuous random variable, we will be using the term, so in case of continuous random variable, we will be using the term probability density function. So this term is particularly used for continuous random variable. And then probability mass function will be used in case of discrete random variables. Okay. So starting off with probability density function. So we saw last time, like probably when we were trying to understand the histograms, we saw how we draw the smoothened histograms in each cases, right? So similar is the case here. So probability density function is drawn by smoothing the histograms. So for example, let's say we have a set of random variable. Let's say it's ages. So we have ages distribution, and if we try to plot the ages, let's say in terms of interval, and we have histograms, and the smoothened out histograms will give the probability density functions. And similarly, when we have discrete random variable, we will be using probability mass functions. So let's say, for example, let's take an example of rolling a dice. So in that case, if it is a fair die, we will be having equal probability for each of the cases, right? So we can get outcomes like 1, 2, 3, 4, 5, 6, and each will be having a probability of 1 by 6 if it is a fair die, right? And if we draw the probability mass function, it will be like 1, 2, 3, 4, 5, 6. So each case the probability will be 1 by 6. Each case the probability will be 1 by 6. So this is just the difference between PMF and PDF, probability density function and probability mass function. And now we have to see what is cumulative density function. So cumulative density function, in case of, okay, let's first cover how the cumulative density function is defined for uh, discrete variables. So here we can take the same example which we took earlier, the rolling of dice. So in that case, probability density function will be, sorry, cumulative density function will be, so here we had 1 2 3 4 5 and 6, right? So cumulative density function in this case will be just the combined probability as we go from the first random variable to the last. So in this case our first value is 1, right? So the in case of 1, CMF will be, CDF will be 1 by 6, and when we take 2 it will be the combination of 1 and 2, so it will be 2 by 6. And then if we go to 3, then it will be having the combined PMF of 1, 2 and 3, then it will be 3 by 6. And similarly as we go from 1 to 6, the final it will be coming at 1. Yeah.
So don't we smoothen the curve, or is it just the values that we plot?
For CDF,
CDF.
yeah, so for CDF, it in case of the discrete random variable, we just like, as you know, it is a constant value in this particular case at least, right? So
Hmm.
we will be having 1 by 6 in the first value, and then it will for second one it will be 1 by 6 plus 1 by 6. So then we don't have to smoothen out. It is like a step increase, right? An increase
Yeah,
of 1 by 6. So we can't smoothen out here, but in case of continuous random variable, yes, we will get a smoothened curve.
got it.
Yeah. So in this case, if we just have to understand what, for example, let's say what is p of x less than or equal to 2. So what all values will be, what will be the value here? So here we have to take p of x equal to 1 and p of x is equal to 2, right? And CDF will give that answer. So CDF will give 1 plus 6 plus 1 plus 6. And similarly, if we look in this particular graph, so this is the value which we are looking for. So below 2, so it will be 2 by 6. And for each value, we can do the similar calculation. And in case of probability density function, that is for continuous random variable, in case of PDF, how is cumulative density function defined? Okay, let's check that as well. So CDF, the definition is similar here as well. It is the combined probability for each random variables starting from the initial value. So here, for example, let's take the similar example which we took earlier, that is the distribution of ages, right? So let's say the age distribution which we have is distributed something like this, a normal distribution. Hmm? So this is our x, this is our x, and this is our PDF. And how will be the cumulative density function? So cumulative density function, as we know, it is the combined probabilities starting from the initial value. So here it will be starting from a small value, sorry, starting from a small value, then it will be increasing, and then it will be going again into a, it will be somewhat like an S-shaped curve. And the slope in each point here, particularly for the continuous random variable, the slope at each point will be giving the PDF value. So that is the importance of cumulative density function. So slope in each particular point will be giving the PDF. So this is the cumulative density function. This again is the X. So here, as you can see, in the starting the slope will be small, and in the end as well the slope will be small value, and in the center the slope will be a higher value. So you can see the how it is reflected, how the PDF is reflected in the CDF. So the concept is very important to understand the area under the curve and the probability density. So the slope, so the main takeaway from this topic, the CDF, is that the slope of the CDF will be giving the probability density function. And similarly as above, which we did for the rolling dice experiment, we can do the calculations over here. Let's say we have a random variable which is the distribution of ages, and the calculation can be done similar here as well. Maybe I can give a small example. Let's say here we had the ages of 40, 35, 45, something like that. And the calculation here also we can do something like less than or equal to 45. Yeah, the calculation is same as how we did in case of probability mass function. And here we know that the probability values will be always between the range 0 and 1, right? So it will be always non-negative. And the total area under the PDF, so the PDF curve will be always equal to 1. So that is the mathematical concept which we have to understand from these concepts. So the CDF value will be, at the final value the CDF will be 1. That will be also equal to the total area under the curve, which is equal to again 1. And the PDF, or the probability density function, will be always having the value which is between 0 and 1, that is a non-negative value always. So with respect to yeah.
So CDF, so the total area under PDF will be 1. And is there anything about CDF? I didn't get,
yeah,
what is the
yeah,
significance of area under the curve of CDF?
Area under the curve of CDF, in case of CDF we are not looking into area under the curve, because there we are majorly concentrating on the slope of the curve. So slope of the curve will give direct information about the PDF. And the CDF, the combined distribution function, density function, will be at the last point it will be equal to 1, because it is the sum of probabilities for a particular event. Yeah, that's the main takeaway there. And now we know the basic terms which we have to take care when we are discussing about probability, right? So the next topic which we will be covering.
Can I just sorry if if I haven't understood it properly. So you said that the slope of CDF at various different points is the PDF. So how does it let's say if we have, let's say, 10 readings, say x equals 10, so the PDF, the CDF curve will be little different compared to if the x is 100 or if the x is 1000. So how is it can I haven't really understood it. What is the PDF? What does it mean when you say the PDF is different at different points? of the sigmoid curve on CDF. There's a sigmoid curve on
Mm-hmm.
the CDF,
Mm-hmm. Yeah.
and you, like, what is the PDF at different points?
Mm.
Like, what is, I don't know if I'm explaining my question properly.
Yeah, your question is completely valid. So, your question was that how we can define the probability density function from a curve like this. This was your question, right? So, the sigmoid curve here, which the S-shaped curve which you are seeing here, this is particularly for PDF which is distributed in case of a normal distribution. So, here in this case we are having the distribution which is almost normal, right? It's a normal distribution which is a bell shaped curve. So in this
Yes.
case the CDF will be of this fashion, an S shaped
Yeah.
curve. And as you can see here, I am like here the value is increasing in a slow range, and here it's increasing in a much higher rate, and then it's again decreasing, and the rate again got decreased. So that is what is reflected here in case of CDF. So when we draw this into a CDF fashion, it will be like, okay, now here let's say we have a value of 0.001. So the
Yeah.
first value will be same as that, and then next here let's say we have a value of zero point 0.02. So here it will be 0.01 plus 0.01 plus 0.02. So this particular value over here, which is corresponding to this one, will be 0.03. So like that it will be going like similarly how we did in case of the probability mass function for the discrete case. Here also it will be the added probabilities.
Yes, my question is, the slope of the CDF will be different at different points wherever we choose, right?
Yes.
Or is it so? What does that indicate? Like, if you choose a point somewhere on the, somewhere in the initial part, the slope is different.
Mm.
At the, like at the end point, the slope is different.
Mm.
Somewhere in between, the slope is like. So what are these different PDFs? What do they indicate? Or uh, I
Yeah.
don't know if I'm asking a very foolish question. I'm sorry.
No, 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 no. Like the question which you asked is how, in initial case here, let's say
Yeah.
here, okay. So if you look over here, this it is slightly starting to increase the probability density function from almost a zero value. It is slightly starting to increase. Similar is the case here. From a small value, it is decreasing, but then the rate of increase here and the rate of increase decrease over here, if we check, it's almost in the similar range, right? Like a small
Okay.
increase and a small decrease. We are
Okay.
just
Okay.
taking the absolute value, and
Okay.
similarly that is reflected over here.
Right. 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 Yeah. Yeah. Sorry. Sorry. Yeah. Understood now. I'm so sorry. Yeah.
Yeah, it's okay, no problem. Okay. Yeah, so the next topic which we will be covering today is different types of distribution functions. We'll start with Bernoulli distribution function. I think most of you will be familiar with the term. We will be covering Bernoulli distribution, binomial distribution, then we will be covering normal or Gaussian distribution. We will also cover Poisson distribution, then we will cover log normal distribution, and then uniform distribution. And if time permits, we will also see the central limit theorem. Yeah, otherwise we will discuss in the next session. Okay, it is very important to understand the probability distribution function, basically because in case of EDA, when we are doing the exploratory data analysis and trying to understand how the data is behaving, this particular area is very important. And there are certain machine learning algorithms or deep learning algorithms which are particularly designed if the data is behaving in a such a way. Most of the machine learning algorithms, it is uh, uh, it is um, it is good when we apply in case of normally distributed data, and most of the data when we which we find in around us is mostly in a normally distributed fashion. So it is very important to understand how the data is distributed. So this topic is a important topic when we cover the statistics for data science. So Bernoulli distribution. So Bernoulli distribution is the simplest distribution which is particularly looking into discrete random variables or discrete probability distribution. So always remember that when we are looking into discrete probability density function or probability distribution, the term which we should look into is PMF. And similarly, in case of continuous, we will be always referring into probability density function, which is PDF. And the Bernoulli distribution, it is a random variable that has exactly two outcomes. So for example, let's say we are taking a situation of tossing coins. So in case of tossing coins, we'll be having outcomes like zero or head or tail, right? So it is an example of Bernoulli distribution. So the next main point is having exactly two outcomes. So here let's say the success, let's say the two outcomes can be defined as success and failure, and the probability for success is always taken as P, and the probability for failure is always taken as Q. And as you know, the probability will be always 1. The total probability will be always 1. So Q will be always 1 minus P, or similarly P will be always 1 minus Q. So these are the main points which we have to keep in mind when we are looking into Bernoulli distribution. So it's a discrete random variable. We are dealing with discrete random variable, and the outcomes will be binary. And if we are looking into a fair coin where we have, let's say we are looking into an example of coins, and the probability of head is 0.5 and probability of tail is again 0.5, and here and here the major parameters, as I said, p equal to, let's like we can take that according to the problem statement which we have. Let's say here I am taking the probability of success as getting a head. So getting head is a success in this case, let's say. So P is taken as 0.5 and Q is again taken as 0.5, and the parameters, the next parameter which we have over here is K being 0 or 1. K is the number of successes. So here, since we are only tossing the coin for only one time, and we can either get a head or a tail, right? So if we are getting a head, then K is 1, and if we are not getting a head, the K is 0. So here, if we draw the PMF, will be having, this is K, 0 and 1. PMF will be like this, 0.5. It will be like this for a fair coin. Similarly, we can have cases with coins not not fair coins. Let's say with probability x equal to 0 is 0.2 and probability x equal to 1 is 0.8. It's a case where the example is not fair. So in that case, probability of 0 will be 0.2 and probability of 1 will be 0.8. And how to calculate the probability mass function here. So there is a formula, it's a universally used formula, which is p raised to k into 1 minus p raised to k. So sorry, 1 minus p raised to 1 minus k, or we can also write p raised to k into q raised to 1 minus k. So let's say, and in this case we can also write q equal to 1 minus p of k equal to 0, and similarly p if k equal to 1, by simply putting the values as we have over here. And if we are looking into the mean of the Bernoulli distribution, we can also do the calculation, but it's a very direct calculation. I don't think we don't have to do that, but yeah, we can. If we apply the formula expected value of x as here I equal to 1 I equal to 0 to 1, k into p of k, here it will be nothing but p. Similarly, the variance is nothing but p into q. And if we are looking into the median, it will be distributed as 0 if p is less than half, it will be 0.5 if p equal to half, and it will be 1 if p is greater than half. So this is the simplest distribution which we see in case of distribution functions, and the mode will be p if p will be the mode if p is greater than q. In case of p greater than q, mode will be p, and else the mode will be q. I hope the mean, median, mode, we don't have to go to the calculation, otherwise it will take much time. So we'll just stick with the formulas right now, and then we'll go to the next distribution, which is the binomial distribution. So binomial distribution is a special case of Bernoulli distribution, or else we can say Bernoulli distribution is a special case of binomial distribution, because in case of Bernoulli distribution, the n value, or the number of times the experiment is conducted, is 1, whereas in case of binomial distribution, it can happen in a sequential manner. So earlier we took the example of tossing a coin in case of Bernoulli distribution, right? So there n was, or there we took n is equal to 1. Here, if in case of binomial distribution, the n value can range anything between 1 and infinity. So here again, this is making into account discrete random variable. So here we will be dealing again with probability mass function, and here it can happen n number of times, and here like the parameters similarly how we had in Bernoulli distribution, we will be having P for success and Q for failure. Here also every output is binary in nature. So here, as I said, the example which we can take is tossing a coin n number of times. Let's say we are tossing a coin for 10 number of times. So that is simplest example which we can take. And here the probability is defined as, probability mass function is defined as P with parameters K, N and P, where N is the number of times which we are repeating the experiment, and P is the success probability, and K is the outcome which we are expecting for, or the success value. So here this is represented as and here the mean median mode, we have to calculate mean median mode here. Here the mean is,
Can you just repeat what is N and K?
yeah, so K as earlier we took K as 0 and 1, right, because it is a binary outcome, so it can be either 0 or 1, and N is the number of times which we are repeating the experiment, and P is the success probability. And here the mean is N into P, and the variance is N into P into Q, and similarly the standard deviation will be nothing but root of N into P into Q. Yeah, so mostly the binomial distribution is used in case of quality control experiments. For example, inspecting 10 items of a factory where to check whether the item is defective or not. Most of those quality control experiments or processes make into account binomial distributions. And there are several other cases as well, but this is the most commonly used use case. And like if you want examples for this particular cases, that we can do, otherwise we can go cover all the distribution. How do you prefer? Should we go with one more example to make the concept clear, or should we cover all the distributions today itself, and then if you need, I can send the examples later. How should we do?
For me, you can send me examples later. I think we should continue the other distributions.
Okay.
That works.
Okay. Then let's do that. So the next distribution which we will be covering is Poisson distribution. So the Poisson distribution is again a discrete probability distribution that expresses probability of a given number of event occurring in a fixed interval of time. So it counts the events if the events occur with a non-constant mean rate with a and independently of the time since the last event. So this is how the Poisson distribution is stated. For example, let's take an example of people going to hospital. So and we are trying to analyze the patients coming in particular interval of time. So in between 1 and 1:30 p.m., 1:30 to 2:30 p.m., like that. So in that case, the distribution of how the patients are coming in each particular interval. So here we are looking into the interval specifically, and we are assuming that there is a constant rate or constant mean in each particular interval. So that's how this particular Poisson distribution is described. So it basically describes the number of events occurring in a fixed interval. So let's take the example which we covered earlier. Let's say we are taking time intervals like this, and the patients are so as I said, it will be taking into consideration an event which is occurring with respect to a particular interval, or so it is very important where we in case of Poisson distribution, we will be taking into account events happening in a specific interval, and here the lambda, it's a main parameter which is used in Poisson distribution. Lambda is the expected number of events occurring at every time interval. So it can be it usually will be a constant value. And if we are looking into the PMF for this particular distribution, Poisson distribution, it is defined as exponential minus lambda raised to x divided by x factorial. And the mean in case of Poisson distribution is nothing but lambda into t, and as I said, lambda is the expected number of events occurring in every time interval, and t is the time interval. So the next distribution which we will be looking into is normal distribution. So normal distribution is a very important distribution. As I said earlier, most of the data which we see in real world will be normally distributed, but not every data, but most of it will be normally distributed. In probability density theory or probability theory, a normal distribution or a Gaussian distribution is a type of continuous probability distribution. So this is the first continuous distribution which we are looking into today. We initially discussed Bernoulli distribution, binomial distribution, then we discussed Poisson distribution. All the three were taking into account discrete random variables. So this is the first continuous random variable or continuous distribution which we are looking into, normal distribution. So as I said, most of the data follows normal distribution, and as we know, the normal distribution, the data will be following a bell-shaped curve, right? And what will be this value? This value for a symmetric, as we discussed last week, for a symmetric case, this center value will be mean, which will be equal to median, which will be equal to mode. And the notation for normal distribution is n mu sigma square, where mu is the mean and sigma square is variance. And we know that mu is a measure of central tendency, and similarly variance is a measure of dispersion, right? So as for example, let's take three cases where we have same mu value, but then but then the variance is changing in all the three cases. So let's say we have three standard deviation, lambda 1 sigma 1, sigma 2 and sigma 3, and it is like sigma 1 less than sigma 2 less than sigma 3. So if we plot that, so the sigma 1, let's say it's something like this. So this is the mu value. And how will be sigma 2? Sigma 2 is greater than sigma 1, right? So the spread will be little bit more. And in case of sigma 3, the spread is still more. Yeah. So it's corresponding to sigma 3, sigma 2, and it is corresponding to sigma 1. Yeah. So in case of Gaussian distribution, we can write PDF because we are dealing with continuous random variable. The PDF we can write it as 1 by sigma root 2 pi e power minus half xi minus mu divided by sigma the whole square. So this is the probability density function in case of normal distribution. And here mu is nothing but the mean and sigma square is variance. And the next topic which we have to cover is
Here, maybe you can just signify 95% of value will be between 2 sigma, those things.
Yes.
Maybe that's are mostly asked in interviews.
Yes, that was my next topics, which is empirical rule of
Sorry.
yeah, it's okay. Empirical
I
rule
thought you
of
are going to distribution. That's why I stopped.
no, empirical rule of normal or Gaussian distribution. Yeah, as Dhananjay said, it's a very important rule because in most of the task we will be asked this question, because when we look into, even when we covered the I guess when we covered the box plot, even there it was important, because when we are looking into data and saying that certain data is outlier and certain data is not significant, all those things, like we will be mainly dealing with this concept, the empirical rule of normal distribution. We'll see what empirical rule of normal distribution is. Yeah, it says that when we draw the data, the normal distribution, let's say we have a distribution this sort, it says that 68.27% of the data comes in the range sigma mu plus or minus sigma, that is 68%. Let's say this is the 68.27%, this is mu, this is sigma, this is sigma again. So 68%, 68.27% comes in the window mu plus or minus sigma, and then when we go to 2 sigma, so this particular range over here, 95% will be in the window 2 sigma, that is sigma mu plus or minus 2 sigma will be covering 95.45%, and then 3 sigma will be covering almost 99.73%. So this is the empirical rule of normal or Gaussian distribution, which says that mu plus or minus sigma will be covering 68.27% of the entire data, and then 95.45% of the entire data will be covered in mu plus or minus 2 sigma, and similarly 99.7% will be covered in mu plus or minus 3 sigma. So if
so why is it called an empirical rule? Like it's not theoretically derived; it's just sort of observed in multiple, examples. Is that what does it mean, or what does it mean empirical?
yeah, it is theoretically proven as well. Like it is something which we can prove by in most of the normal distribution cases. But if we have to look into the proof, it will take some time. Maybe I can send you the proof later. And
No,
this
not needed. I mean, I just wanted to know whether it's theoretical entity, or I mean, sorry, it's just purely empirical or something like that. Because many times normal distribution is an ideal. We
yes.
can you have to have infinite observations to have a truly normal distribution. So I don't know. I'm just sort of just a thought that crossed my mind.
Yeah, actually it is mostly based on what to say, the observed data. So as I said, most of the data which will be following the normal distribution, right? And when we look into the data which are having higher in number, for example, most that we will be seeing more detail how this is more important when we look into the central limit theorem, where we will be seeing, let's say, if say the number of data points is more than 30, so that is
Okay.
something which is counted as, which is higher in the range. So if the number of data points is greater than 30, and then it is more likely that if we make those some sort of manipulations, then that data can be again made into a normal form. And
Understood.
this observation, as I said, is mostly based on the empirical findings. And
Okay.
I guess there is some sort of proof, but I don't know whether it is completely theoretical.
No,
Yeah.
no, I'm not interested in. I mean, I just wanted to have your thoughts on that. That's all.
Yeah.
Thank you.
Yeah. So, yeah, so if someone is asking the question like, what is the probability of mu minus sigma less than or equal to x less than or equal to mu plus sigma, so without any calculation or anything, we just can write it as 68%. Similarly, if we are asked mu minus 2 sigma less or equal to x less than or equal to mu plus 2 sigma, we can write it as 95% and probability of mu minus 3 sigma less than or equal to x less than or equal to mu plus 3 sigma, we can write it as 99.7%. So this is basically normal distribution. Similarly, we have standard normal distribution. So standard normal distribution is a specific case of normal distribution where we will be restricting our values of mean and variance. So in case of normal distribution, sigma and mu can take any value, but in case of standard normal distribution, it is particular that mu should be 0 and standard deviation should be 1. Every Gaussian distribution or the normal distribution can be converted into standard normal distribution. So this type of transformation is done using a particular score called Z score, and this again is an important topic which we will see because Z score calculation and standardization, so those are important topics again, because some machine learning algorithms, they are specifically designed to use data which are distributed in a standard normal distribution. Z score is nothing but xi minus mu divided by sigma. So for example, let's say we have random variables like 1, 2, 3, 4 and 5, and in this case the Z score will be, as I said, it is xi minus mu divided by sigma, right? Here the sigma is nothing but 1 and mu is 3. So if we do the transformation, the y value, which are Z score or the Z transformed x values, is nothing but minus 2, minus 1, 0, 1 and 2, and the distribution will be looking like this, with mean 0 and standard deviation 1. Here let's say we transformed x into standard normal distribution with mu equal to 0 and sigma equal to 1. What's time now? Okay, it's 5 6. Should we conclude with normal distribution today and start then on the next day, or how should we do?
I have some more time, but at 9:40, right? Maybe everyone will have some other things. Maybe one of the weekdays we can finish off inferential descriptive statistics if you are available, and then start with descriptive inferential statistics.
Yeah. We can maybe on this Tuesday or Thursday. I mean, I can do the session. So if everyone is available on any of those dates, like we can do a poll later, and accordingly we can arrange.
Yeah.
I guess it will take another 45 minutes to cover. We have uh, three more distributions, and then we have to also cover the central limit theorem.
Yeah.
Mhm. Yeah. Anyway, we will make a conclusion to this normal standard normal distribution. So now we saw how but if we are given a distribution, how to transform that into a standard normal distribution. And let's say you are asked, let's say we have a question like how many standard deviation away is 4.5 um, from the mean. So we are taking this we are taking a similar distribution like earlier. We have 1 2 3 4 5 6 7. Let's say this is our data, and it's something looking like this. The distribution is something looking like this. 7. And you are asked the question, how many standard deviation (4.5) is away from the mean. Here in this case, if we do the Z score, it will be 4.25 minus 4 divided by 1. Here the mean is, in this particular case, the mean is 4 and the standard deviation is 1, and the answer is 2.5. So the answer is 2.5 standard deviation away is 4.25 from the mean. So this is how we should interpret the standard normal distribution when we are asked these type of questions. And the Z score and the standard normal distribution, it is basically, it is important in certain cases, as I said earlier. In some of the machine learning algorithms, for example, when we are applying Gaussian in the standard Gaussian, in certain cases it is important that the data is distributed in a standard normal distribution. So it is important to understand what is the concept there and how is this Z score calculated, how each data value is transformed into a standard normal distribution. So these are important in certain cases, and we will look into detail how the Z score is made use in the in more detail in case of the inferential statistics, where we are looking into hypothesis testing and everything, and that we will cover in coming sessions. Maybe next to next sessions we will be covering hypothesis testing and inferential, like most of the topics in the inferential statistics, and there will be all again using the Z score and different other transformation methods. Yeah, I guess maybe we can conclude conclude for today. This were like today's class. I guess it was mostly yeah, there were so many new terms